Okay, class, let's get started. So, in the last time we have looked at convergence in distribution and convergence in probability and convergence almost surely. These three are different concepts. And what we have looked at is that the convergence in almost surely is the strongest convergence, and convergence in distribution is the weakest convergence. And we have looked at the several limiting theorems, weak law of large numbers and strong law of large numbers and central limit theorems. So these are dealing with the cases when we have this sequence of random variables. So now, suppose that let's say we have a function of random variables. Let's say continuous function of random variables. And now we are consider that we are combining with the two random variables, one converges in distribution, one converges in probability. Then how can you drive the result from these complicated situations? Today I'm going to look at the cases I'm going to look at these cases. Let's say we have a function g, which is from r-dimensional real vector space to the real number space, and it's continuous. When xn converges almost surely to x, then g sub xn converges almost surely to the gx. If xn converges in probability to x, then gxn converges in probability to xgx. If xn converges in distribution to x, then gxn converges in distribution to gx. So if you apply the continuous functions in the sequence of random variables, if original random sequence of random variables has convergence, then for continuous function of the sequence of random variables also converges into the function of the x, which is the original result from the convergence from the xn. So proof of this theorem is omitted. And thus we have a corollary. So let's say xn converges in probability to A, the xn and yn converges in probability to B, where A and B are constants, then xn plus minus yn converges in probability to A plus minus B. And the product, it also converges in probability to the product of the constants. If B is not equal to 0, then xn divided by yn converges in probability to A divided by B. So I think this is a pretty straightforward result. Let's say y1, y2, yn with the expected value of u and variance of yi sigma square, which is finite. And let's consider Sn tilde square, which is the MAD of the sigma square. Sorry, that the MAD of sigma square is under normal distribution function. So let's say n. So 1 over n times sigma square I to the 1 to the n yi minus y bar square, which is you can express as the 1 over n times the sum of I equal to 1 to n yi square minus y bar square. By with low large number, y bar converges in probability to mu. Mean of yi square is converges in probability e to the y, where sigma square plus mu square in probability by probability n and by y bar square converges in probability to the mu square. Corollary A, since we have the sum of yi square divided by n converges in probability to sigma square plus mu square, and y bar square converges in probability to mu square. So by using the corollary that we just have taught, you can just take a subtraction mu square plus mu, sigma square plus mu square from the mu square, so which is the sigma square. So your Sn tilde square converges in probability to the sigma square, example, so Sn theta square is the, if you get Sn square, so Sn square is the sample variance. So your sample variance is the Sn theta square multiplied n divided by n minus 1. And n divided by n minus 1 equal to 1. So second corollary, you use the multiplication. So if you have convergence in probability, two sequences of these random variables, convergence in probability A and B, and product of the sequence of random variables converges into probability to the A times B, which is original Xn, and original is each sequence of random variable converges. So this Sn square is n divided by n minus 1 times Sn theta square, and n divided by n minus 1 converges to the 1. So by corollary B, Sn square converges in probability to the sigma square. So Sn square and Sn theta square has the same limit in probability. Let's introduce a very important theorem in large sample theory. It's called Slutsky's theorem. Let's say An and Bn converges in probability on A and B, respectively. A and B are constants. And Xn, let's say Xn converges in distribution to X. Then An times Xn plus Bn converges in distribution to A times X plus B. So the linear combination of convergence in a sequence of random variables that converges in probability and converges in distribution. It converges in the distribution to the linear combination of the target distribution x times the target constants A times X plus B. So the linear combination is preserved in terms of convergence in distribution. So I mean, this is very important theory in the large sample theory. Let's get an example. Sn is the square root of Sn squared, which is the sample standard deviation. So we want to find asymptotic distribution of x square root of n times Xn sample mean minus mu divided by Sn. So usually, if x has a normal distribution, then this form, square root n times xn x bar and minus mu divided by Sn follows the t distribution. But we don't know the distribution of xi, so we would like to get the approximate distribution of the sample mean. So we know that by central limit theorem, that x bar n minus mu divided by sigma divided by square root of n converges in distribution to the standard normal. And by previous result, sample variance converges in probability to the population variance. And based on that, sigma divided by Sn converges in probability to 1, because if you divide by 1, 1 over 6, so this is 1 divided by Sn square converges in probability to 1 over sigma. So if you divide by sigma square is constant, so it converges in probability to 1. If you take a reciprocal on each one, so one reciprocal 1 is still 1, but 1 over reciprocal of Sn squared. Sigma squared is the sigma squared divided by Sn squared. So this is sigma squared divided by Sn squared converges in probability 1. And this is, you take a square root of that, and by continuous mapping here, sigma divided by Sn is converges in probability 1. So hence, if you express this original distribution that we are looking for is equal to sigma divided by Sn times square root n times xn divided by mu divided by sigma. This converges to 1. It converges the distribution to 1 times z, where z is following standard normal. So it's going to be z, which is the standard normal. So in the large sample, with the large sample, your standardization with the sample mean and the sample, mean with population mean and sample the sample standard deviation converges in distribution to the standard normal distribution.